Grade 12 Physics, Dynamics Note number 11, Banked Curves. Here we're going to apply circular motion to an on-ramp scenario. So it's basically going to be a car going around a traffic circle, but the traffic circle is going to be on an angle. So providing a little bit extra circular force or circular centripetal force for that car as it's going around. So if we take a look at that on-ramp, so this would be taking a slice of it where the car is traveling out of the page. The on-ramp will be in a circle. Okay. So this would be a car on the on-ramp trying to get on the highway. Gravity is down. Normal force, again, is perpendicular to that on-ramp. There's the radius for the car. It would travel in a circle at that radius. Now the question is, if the radius is to the right, how do we get a centripetal force in the direction of that radius? FG is exactly perpendicular to the radius, so we can't break the FG up. We're actually going to have to break up the normal force into two components, one towards R and one that's going to balance FG. So there's Fn of X and there's Fn of Y. Those will be balanced, and there's our angle theta for the normal force. Let's do a numerical example, bank curves. So here, a car is going to go around an icy or frictionless bank curve. So the reason why that's important is because if the car goes too slow, it'll actually slide down the curve. If it goes too fast, it'll spiral up and over the top edge of the curve. There is a magical speed a car can go on a frictionless curve where it can just stay at the right height. So if the bank's on a 20-degree angle, how fast does the car need to go? So here's the bank curve. We'll just draw a box for the car. FG will be down, normal force, again perpendicular, and we'll break that up into the two components. We know that F and Y is going to be balanced with FG. So here, Fnx is acting as the centripetal force for this ramp, which has a 50-meter radius. So let's take a look. F equals ma. So F in nx equals mv squared over r. But what is Fn of x? We can relate it to Fn of y through tan theta. So tan theta equals Fnx over Fny. So Fnx equals Fny tan theta. Now that's important because we know Fny is equal to mg. So we can sub that in. That's something that we know. So mg tan theta equals mv squared over r. Here again, the masses don't matter, so it actually doesn't matter how heavy that car is. We solve for v, so it's rg tan theta. As I said, the radius is 50. G is 9.8. And the angle will be 20 degrees, which gives us a velocity of 13.4 meters per second, or 48 kilometers an hour, which is reasonable for an on-ramp.